When technology had just begun turning digital, we were there, pushing the boundaries of system innovation, helping transform the most advanced and demanding technical industries, while enabling completely new ones that are now redefining the way we imagine the future. Unleash imagination. Turn great ideas into reality with Cadence.
Well, thank you so much for that introduction. What we'll be spending time on for the next 45 minutes or so is a case study that we have done based on the Wild River platform presented earlier. And we'll be showing a measurement to simulation correlation and also share with you some of the learnings that we have gotten throughout this process. The agenda for today is we'll first talk briefly about motivation, talk about the test vehicle that we chose, and then we have 3 sections following that. The first part is related to material property identification. We'll then jump into a section talking about S-parameter correlation, talk a bit about channel metrics and TDR response correlation as well for a few of the cases that we have simulated so far. And then we'll talk about some of the correlation challenges in the third section of this presentation. And that will cover influence of connectors, it'll cover influence of manufacturing tolerance and variation, and then we'll talk also about the importance of the boundaries defining the size of what you're simulating and the conditions, the boundary conditions you apply on that. And then we'll end up with a summary and going to the Q&A session. So the objective here is, at the moment, Clarity has been used by many design teams to address signal and power integrity challenges. And Clarity allows people to solve bigger problems than they have normally been able to solve with a 3D FEM solver. And that has basically allowed them to reimagine how they apply finite element method to their design process. Naturally, trusting any EM extraction to 50 gigahertz and beyond really requires good correlation to measurement methodology. And that's what we'll be talking about here based on the Wild River CMP 50 platform that was presented by Al Neves earlier in this seminar. And we're going to be looking at correlation between 40 and 50 gigahertz and talk about the topics that I mentioned already in the agenda slide, including material property identification, correlation challenges, influence of connector models, and manufacturing and tolerance variation. So Clarity from a methodology standpoint, to those of you who are not familiar with Clarity, the FEM method is basically taking a 3-step approach. And this is shared across pretty much all of the FEM solvers available in the industry. You take some geometry imported either through MCAD or through an electrical design like an electro database. And within the first step, an initial mesh is created. The next steps in the solve process is then to adapt the mesh so you resolve the areas of electromagnetic importance for the given structure. In other words, what's happening is that the mesh density is increased in the area where you have field that is important for the particular structure. And what is then done is that the S parameters between consecutive iterations is compared, and the process stops essentially when the convergence criteria is met, which is typically the change in the S parameter from one step to the next. And then the third step is the frequency sweep. And again, all of these 3 steps are shared amongst FEM solvers. So you might ask from Clarity, what is really new, what is being brought to the table here that's not existing in the market today? And that's shown in the next slide, which is we can separate this out into 4 groups, especially, well, starting here on the upper left. One of the things particular to Clarity is that it integrates directly into the design environment. So whether you're working within the Cadence design environment for IC, for package, for board, It's possible to launch Clarity directly, get results back that helps you guide the design process. And you don't have to think about all the setup related aspects and the back annotation and so on. And this also actually applies across the microwave design environment from Microwave Office. The other aspect, and this is actually one of the key enablers for allowing you to simulate bigger structures, that's the massively parallelized matrix solver that we have added on top of Clarity. So essentially what it does is that it takes the very big matrices that are typically built up by FEM solvers and distribute that across multiple machines through this parallelized matrix solver. And the nice thing about that is that traditional FEM, you're limited to how much memory you can have on a single machine. That sets the limit for how big a project that you can actually solve. With Clarity, because of this parallelized matrix solver, you're not confined to be on one machine. The entire matrix doesn't have to be within the memory of one machine. And that means we break free from that limitation factor in other FEM solvers, which is that the matrix must be within the memory of a single machine. So that typically what we see is people push into like 1 terabyte machines, 2 terabytes, but it still may not be enough for what they need to be doing. And that's really what sets Clarity apart a lot. And part of this matrix solver is in fact the ability also to use different compute architecture sizes. That means if you have a farm, you can basically scatter the project across many different machines that may or may not have the same number of CPUs, the same amount of memory, and so on. So it allows you a lot better scalability. And finally, the matrix solver is also fault tolerant. So if any computational node goes offline or other things happen that may happen in, say, in a cloud environment, it can directly recover from that. And the other nice aspect of that, of course, also is that if you can use different size machines, you don't have to go for the biggest one, and that allows you to minimize the cost if you're taking out cloud resources from, say, Amazon Cloud or something else. So that was just a quick introduction of Clarity. Let's go in and look at the actual test case that we will be working on. So this was already introduced in the beginning talk here, but just reiterating in case you came in just for this presentation or later than the initial presentation. What we have selected for benchmarking is the Wild River Technology CMP 50 platform, which is essentially a 50 gigahertz advanced channel modeling platform. The target application is to allow you to, in a consistent manner, get correlation between the EM solvers that you're using and measurements. And it combines 27 different structures based on primitives for calibration tasks, for VNA gating, time domain transforms. It has a number of very lossy structures. There's resonators, multi-impedance structures, wire fields, and so on. And the particular sample that we are looking at was assembled with 2.4 vertically launched female connectors. So that will take us up to 50 gigahertz in bandwidth. So whenever you have such a correlation task, you want to correlate up against measurements. There's a lot of things you need to consider to go to 50 gigahertz and beyond. And the prime points are listed here in this slide. The first point being material identification. You really got to be sure you have the right properties that you use for both the dielectric values, the surface roughness, and of course also the stack up dimensions, the height and the trace etching and so on. In addition to that, there's some specific items related to the EM solve setup, such as defining what region you want to simulate, the boundary conditions you're going to apply in that region, the solution settings, convergence settings that you use, as well as the connector models that you use. And of course, for getting the phase right, also you need to worry about the connector calibration plane. And lastly, but this is also very important, you always have to come back and think about manufacturing related topics, not just from a stack up, as was already mentioned, but also from tolerance perspective. What is the tolerance on, say, the stop of your, if you back drill the bias and so on. And in fact, this particular structure here, we'll come back and talk about that for the initial correlation. But the first item we need to spend some time on is the material identification. Before doing that, though, there's just a few points that I want to emphasize here in the beginning. What did we do to set up this project to begin with? Well, basically, we're using the electro bolt imported directly. We modified the cross-section to match the results that came out of the cross-sectioning report from the test lab. So that means adjusting the stack-up thickness, adjusting the trace cross-section. That essentially means you're going to have etching of the traces. You can either simulate with etching, which is going to have some expenditure in terms of additional mesh elements, or you can use an average width for the traces and just assume them being rectangular. And that's actually what we did in this particular presentation. For the bias, all of the simulation results are simulated with a 7 mil back drill stop, which is the nominal back drill. And here's an example of back drilling from a wire that goes from top to layer 3 in this 8-layer stack-up bolt. And you can clearly see the stop sticking out here and the actual drill used for the back drilling. Same here, where we have routing from layer 3 to layer 6. For the DC related aspects, or rather the plating, it's basically ignored in this case. We're only correlating from 40 megahertz to 50 gigahertz. So the plating itself, the DC correspondence is not that important in this case. And lastly, in terms of launching the signals into the structure, we are looking at different types of connector modeling, both including mechanical CAD data from the manufacturer, as well as a few other methods that we'll talk about. Okay, so for the material identification process, this is based on structures that are available already on the Wild River board. There's 2 strip lines for basically a 2-inch and an 8-inch strip line, and the same there is for microstrip material identification. And the process uses a generalized S parameter to de-embed out the connector launches from both simulation and measurements. And then we compare simulation and measurement for that idealized transmission line and adjust epsilon relative and the loss tangent at a low frequency until we get a good phase match between measurement and simulation. Second step is then we add a surface roughness model and adjust until we minimize the magnitude difference in insertion loss. And then finally, a few more fine-tuning points can be done in order on epsilon relative and the loss tangent to minimize the remaining differences. So the first item here, and I'm not going to cover this in a lot of detail, I'm going to provide some references, but that is deriving this generalized S parameter. And this is based on the following approach. So we have 2 transmission lines, a long and a short transmission line. So I call the short one TS and the long one TL. And T here is the transmission matrix. So you can see the short structure, it has a launch at both ends. Then you have the line. You can basically break that in half and say one side has the launch plus 1-inch transmission line. The other end has 1-inch transmission line and then the connector launch. That's how you can describe that. So the short segment transmission matrix basically becomes the product of those 2. Assuming the launches are identical between the long and the short launch, the long line can then be split up into identical sections, and in between there is a generalized transmission matrix for the pure trace. And that means it's going to be normalized to its own reference impedance. And this is what's shown here. I'm not going to go through the mathematical details. Again, there's some references here, but the main point is with the generalized S parameters, we end up with a representation, an S parameter representation of the transmission line, which has 0 reflection. And then the through term is basically just a function of its complex propagation constant times the length. DL here being 8 inches minus 2 inches, so it's 6 inches long. And that is what we are comparing now as we go into the material fitting part. The material fitting is monitored in both in terms of looking at insertion loss, but also in terms of looking at the derived effective dielectric constant. And this is based on just looking at the phase of this generalized S parameter for the TG matrix or the transmission line matrix, and then deriving the effective dielectric constant. And that is what you will see here in this slide. So basically, the first step, as mentioned, is we are adjusting the dielectric constant and potentially the loss tangent of the dielectric material until we minimize the phase differences. And this is shown here as we're sweeping through different dielectric constants. And you can see in this particular case, we're looking at the insertion loss magnitude, the insertion loss phase, and the effective dielectric constant. And the lower row here just shows the difference between the measured results in orange and the simulated result in blue. So you can see as we're sweeping through the dielectric constant, we're basically going from 400 degrees phase difference down to around 50 degrees or so by just changing the dielectric constant. But what is very evident is that we're not meeting the magnitude at the moment, and that's because the surface roughness plays a very important part, and that is then the next slides we'll talk about. What we're going to be using for this particular case is we're going to be using the Huray surface roughness model. This surface roughness model has two parameters to it. There's the surface ratio, and then there's the radius of the nodules that are being used for this model. So when you look at the model, this is typically defining some stack of balls or nodules, spheres, and it has a certain number of layers. And for the particular model that we're going to be using what's called or commonly referred to as the Huray cannonball model, which stacks or has an array in the bottom of 3 by 3 balls with radius r. And then we stack a total of 3 layers. So we have a total of 14 balls in the stack. And when you then calculate out the surface area that they cover versus the surface area of the spheres, we end up with a surface ratio of around 4.9. And that's what we'll be using. So we just have one value to sweep, which is the surface, or sorry, the radius of the nodules. So the radius of the nodules or spheres in the snowball model here needs to get some data from, say, the data sheets. And typically in data sheets, you're going to find a couple of different values depending on the material you're looking at. There's either the 10-point mean, the average value, or the RMS surface roughness value. And per the reference stated in the bottom of the slide here, the radius of the spheres in the cannonball model can be approximated as 6% of the 10-point mean value. And that'll come out to be also derived then from this, or related to this number RQ as well, which is going to be the height of the stack overall. When you apply the surface roughness model, you can actually mimic what happens in manufacturing, where you have a drum and a mat side. Each of those are going to have different surface roughness. You're also going to have surface roughness on the sides of the traces. What we did in this particular case is just to use an average value for all of those within Clarity. And now we're going to sweep through that radius of the spheres, which is what you see in the slide here. Oops, sorry. So basically, you can see as the radius of the sphere goes up, you're also coming closer in terms of the insertion loss match. And what you can see, if you notice the phase difference, this is actually set up such that we're monitoring difference from 0 to 30 gigahertz and from 0 to 50. Overall, as we go through the second step, you're going to end up with around 30 degrees difference to 30 gigahertz and around 45 or so to 50 gigahertz. And this difference we can actually minimize again now that we have added the surface roughness. We know that's going to add some delay. So what we can do is we can slightly tune the dielectric constant in the third step, and that's where we end up with the model that you see here. So overall, for the strip line that we are using here, we get very good match up to 30 gigahertz. You can see in the insertion loss, it's within 0.5 dB total span difference between the measurements and the simulation. And also the phase difference is very minimal, even up to 50 gigahertz. It's within 15 degrees or so. So very close match. But the one thing you will notice, and this is going to play a role as we go into the third section of the presentation, is the deviation at the higher frequencies. These are basically higher order modes that we need to look at as well. We did a similar process for the microstrip. So as mentioned, this stack up is 8 layers. And what we assumed as we matched the material model for the microstrip is we assumed no coating layers, nothing. We just assigned everything to the layer between the top metal layer and the reference layer on the second layer in the stack up. And that's going to have some impact on some of the results we're going to see for the microstrips. Anyway, the focus for this correlation task is we typically see most serial link is going to be routed anyway on stripline layers. So that's going to be the most important part. But this work could be refined further by adding coding layers and things like that to the modeling. So let's talk about the correlation to measurement. So we already talked about some of the key aspects here, but one thing that's really implied is that whenever you take the structure and you want to get out extracted results, you're assuming that the FEM solver will actually properly adapt the mesh in the areas of relevance for your particular structure. So when we look at this structure, which we'll investigate first, this is actually emulating, if you will, a launch where you go from a ground signal ground at this end to a single-ended mode. And you're going to see that, of course, if you have edge launch connectors or in a lot of other configurations where you go from one mode to the other. And the assumption is, of course, that the EM solver is able to find, again, what's electromagnetically important. So let's have a look at the mesh. So the mesh adaptation in the FEM solver is basically you first apply an initial mesh that is purely based on the geometry. And the structure we're looking at here is a total of 3 inches long. That is the wavelength at 50 gigahertz is what the length that you see here. So you can see in terms of the initial mesh, this is based on geometry. We have nodes wherever there's nodes in the layout. So if we have here the grounds, of course, it applies or attaches to those edges here. We also see the transmission line itself. We have the tetrahedral elements, and this is based on the geometry alone. But naturally, what's going to matter is going to be the frequency content. So what Clarity will do is that it'll apply a frequency-based adaptation of the mesh, plus also automatic seeding around the transmission line segments. And so the result from that is you can see you now get a lot finer initial mesh to start out with in the Clarity solution. And you can also see that now the mesh element size is more comparable to the wavelength here. And after, then it goes through a number of iterations until it meets your convergence criteria. And that's what's shown in the next slide here. On the left-hand side, you can see the mesh, the final mesh in this case, and you can see there's a lot of density around where we have the actual trace. And if we take a closer look here, obviously you would expect the mesh to be very dense around the trace itself, but also along the areas where you have a lot of field action. And we expect here that you have a lot of field activity around where you have the gap coupling. And then as we go further and further away, you would expect that the mesh becomes coarser and coarser because it's really the main things that are happening is in that area plus along the trace. And that's indeed what we see in this case here. And then in terms of monitoring the quality as you progress through the adaptive mesh process, you can see here the adaptive or the change in delta S as we go from iteration 1 to 2 to 3 and so on until it meets whatever convergence criteria that you set. So in this particular case, we actually used quite tight convergence criteria because we wanted to be sure we could do a good TDR as well. And that's, again, another topic we'll come back to and talk about a bit. But generally, what you're expecting is a nice monotonous trend towards your convergence criteria or good mesh adaptation. Now, for every iteration, of course, you could run a frequency sweep also. And for understanding convergence and how far you need to go, it can be very insightful to actually run a frequency sweep and see what happens as I go from the initial mesh to first iteration, second iteration, until I reach the converged solution. And that's what you see here. So generally, as the mesh is refined, we see more and more or better propagations end to end. And that is indeed what's being shown here. Also, you can see the phase. There's some minor change here out of these almost 1100 degrees. But the primary change is actually going to be on the insertion loss magnitude as well as the return loss. So for this particular sake, because there's a lot of stuff going on in the return loss, we're just plotting up to 20 gigahertz in this particular case. And what you can see is as we start with the initial mesh, there's relatively high reflections. And then as the mesh is refined and the whole structure is resolved, you see the return loss gradually coming down to the level of representing the actual structure. So you always want to keep in mind what level that you need to meet in terms of the return loss when you run through these adaptive passes here. Now, comparing this to the actual measured results, we see the following correlation here. So the final converged mesh is shown in red, and we're looking at the insertion loss to 50 gigahertz, and the measurement is shown in green. And what you see in this particular case is that up to around 25 gigahertz or so, we are within 0.5 dB to the measured result. As we go beyond up to around 45 gigahertz or so, it stays more within the 2 dB range. And then at the highest frequency here, we start to have some moding effects again that will play a role in terms of the insertion loss. But overall, this is actually really good agreement, especially considering the fact that we are not including the top layers or the surface treatment on the microstrip layer. And that will actually play a role directly in the gap of the transmission line where it couples over to the ground planes. And that is actually what's causing the shift here. And we believe also that's what's causing this some deviation here in the amplitude. The phase itself is within 40 degrees out of 11,000. So that's a tiny error. So overall, considering again that we didn't include the fill in the dielectric modeling, we consider this to be a really good correlation. Looking at the return loss, we see a similar picture from the point of view that the return loss agreement, the trends in the return loss are very close. It basically mimics the same behavior with a few exceptions here. The return loss is higher in the range from 5 to 15 gigahertz. And again, some differences around 40 gigahertz. And this is in fact related to the connector modeling and the exact transition region that we'll be looking at in the third part of this talk. Considering that most SI related specs have return loss requirements in the region of -10 to -15 dB, overall, this is considered to be very good agreement. Now looking at a time domain view, there's a key point to be aware of. So when you're adapting on the S parameters are representing only the terminal behavior. It's not displaying for you what's happening inside of the actual structure. So what you see as we go through the adaptive iterations is that initially the impedance of the lines, so we are launching a signal from here into the structure and then out, is going to be estimated as lower, but then as we get up to the converged mesh, you can now see we get pure transmission line behavior in the final mesh. We then get the capacitive loading in this area, and then it comes out to a longer transmission line section with a slightly rising trend, which is due to the losses decreasing for the lower frequency content.
So overall, the agreement between the measured and the simulated TDR is really excellent. What you could think of as strange behavior in the TDR from the measurement is actually due to variation that is production related, including etching effects, including the via stitching to the ground planes, and also the fact that epsilon relative tends to vary within 10% or so across a board, as was explained earlier by Al in his first presentation.
Overall, the findings here are we have good agreements of trends and values. The insertion loss is very well aligned, again, considering that we have not included everything in the film material, in the material processing. And also the return loss, as you saw, is probably the most sensitive parameter, you could say. The mesh iterations generally drive the R lower, but we have some bands we might want to explore more. And that's where we come in and we'll talk about the return loss variation with connectors and a couple of other parameters. And then we saw also the TDR converged results are behaving as expected. So we want to go in and explore in the third part the reasons for the variation that we are seeing, but overall, again, this is considered to be very good agreement given the assumptions that we have made. I just want to take a few more structures just to give you a better idea of the kind of correlation we are getting between measurements and simulation. So what we're looking at here is a microstrip structure again, but we don't have any edge coupling that could be have requirements for properly modeling the fill-in on the top layers or the solder mask. Basically, what we're looking at is the launch through the connector, and the launch goes to the backside, and then there's this transition here, which has been tuned to give the best transition, the best balance between capacitive and inductive behavior in the wire, and then it comes to the top and then back to the connector here. And what we're looking at here now is the insertion loss magnitude variation, which is very well in agreement up to around a bit above 40 gigahertz. And since we don't have any stops of the wires here, this is going to be related to moding in the design, and we'll give you some idea about what could happen with moding in the structure. What will it actually look like? What is the cause of this? Then looking at the return loss, the overall trends are very good, in very good alignment. There is, again, a bit of gaps here, which is not going to matter probably for a lot of SI applications, but it's still interesting to know what's causing this. And again, we'll link that back to the discussions on connectors. And finally, looking at the insertion loss, you can see that's also in insertion loss phase, sorry, that's also in very good agreement here. Another interesting structure, actually, this is staying with the microstrip. For those of you doing some of the more advanced DDR, in some cases you are forced to go with some tap routing. This is not exactly for tap routing applications, but it does help to show the kind of resolution you get with clarity. So what you can see is we have the launch, we have going to the bottom side of the stack up, we have a few very tiny taps and tiny taps here. This is actually set up to resolve different TDR front ends. What we're looking at here, though, is just the measurement to simulation correlation. And what you can see is that the overall response for insertion loss amplitude, for phase, as well as the return loss itself, is really in excellent agreement. And here's the structure you won't typically see in SI related applications. However, we included this because it is actually really interesting to see from the point of view that we very often see resonances that are caused by wrong placements of wires or interaction between wires, interaction between signals and planes and so on. And so we wanted to see what kind of resolution we would get for resonant phenomena. So if you're doing RF, this is definitely even more relevant example. Essentially what we have is we have a strip line, we have a ring that will resonate. It's directly connected at this very small point here along the edge. And we're just looking at the insertion loss, return loss, and the insertion loss phase again. And what you can see is that we capture very well the insertion loss, or the dips in the insertion loss. And again, as we go into the range of around 30 to 35 gigahertz, we start to see more deviation, but we're pretty certain that that has to do with the exact geometry in this transition here. And at the moment, we are just using averaged dielectric models. So we cannot see, for instance, the predominant resin that's going to flow in the gap here. So consider this is also very good agreement. And the last one we want to show is a very long transmission line. This is the longest structure on the board itself. And we just wanted to see how close we could get to the measurements with a simple launch. So instead of using the complex connectors that we've used so far, we just had a simple launch here to see what kind of correlation can we get with the simple launch when we look measurements or compare measurements to simulation. And that's what you see here. So up to 25 gigahertz or so, there's very good agreement. We believe the deviation as we go to the higher frequencies is in part because of we simulating this with 7 mil stop. We're simulating this with a simplified launch. And in addition, if you look at the phase here, the phase around 43 gigahertz or so start to deviate a lot in the measurements. And that's coming from moding effects that we will also be looking at. So we want to quantify that a bit later as well. And using a simplified launch, you're going to see more deviation in the return loss behavior. So if you want to get closer correspondence, it's likely that you would need to have the full connector models. This is all stuff that will be available in the report we're going to create for this project here. Actually, looking at this structure, we have a lot of insertion loss. 28 gigabits per second in NRC, or running, well, 56, which it would probably be designed for here, is going to be highly infeasible because that's going to have a knee frequency around 28 gigahertz. So you end up with an insertion loss around minus 37. And you need probably, if you can't find it, you need a lot of correction of that signal. So what we did here, just for comparison purposes, was to push down the frequency and just run a simple 28 gigabit per second NRC signal through, and just compare the waveforms to see roughly what would we be getting out if we are looking at the eye diagram comparison between measurement and simulation at 28 gigabits per second. And you can see overall, this is really in very good agreement between the measurements and the simulation. So let's look a bit here in the last step then on correlation challenges. So we've already alluded to a number of the challenges along the way. We're going to be talking about each of the items step by step here. So first part is related to manufacturing tolerances. There's just one we'll look at, which is the stop effect. The other part we'll look at is the connector modeling. What are the kind of connector models available? What are the kind of trade-offs that you're making using one over the other? And then finally, we've talked a lot about moding effects. So what are moding effects, and how does that relate to the boundary conditions that we apply? Starting out with the manufacturing tolerances, as I mentioned initially, we have a nominal drill stop length of 7 mil, but that's actually with a tolerance of plus or minus 5 mils. And what we have done in this particular case is that we've taken the simple 2-inch line that we used for the material identification, and then we simulated with nominal stop length, 2 mil stop length, and 12 mil stop length, and then plotted against the measurements. And what you see in this plot here is we start with the 2 mil stop length, you can see 2 mil stop length has less insertion loss, less dominating effects from the stop naturally. And you can see it's also quite far from the measurements. As we go to 7 mil stop, the nominal stop that we simulated with, you can see even here, the ripple is actually less than it is in the measurements. And then as we push to the 12 mil stop, you can now see it actually matches more or less the ripple on this particular trace. So it's important, a key important takeaway here is really to say that when you're looking at the drill depth or the stop length that comes out, this can have a very severe impact on the predictions that you're making as well. So always keep that in mind when you're running correlation up to 50 gigahertz and beyond. On the connector model side, generally we are faced when you're doing extractions, EM extractions, you're faced with a number of trade-offs you need to make. Maybe in the beginning you don't really have full information about the connector you want to use, or maybe you have no information yet. So you need to start in a simple place. So if you think of a hierarchy of connector models, starting from what's easy to what has highest fidelity, there's a way of simulating the layout even without having any detailed connector model, which will give you a starting point. Then another alternative you could use would be for connectors that are just single signal that looks like a coaxial cable, or try to match as closely as possible to coaxial cable. You can actually just apply a coaxial cable port. And this is useful for instance, getting the right reference plane in your simulations with minimal effort. The last options you have are for getting something that's closer to the actual connector that you're using. And that means downloading the CAD model from the vendor website and manipulating that, or it could be getting a connector model from the manufacturer that contains all of the electromagnetically relevant information, maybe even have the mated part of the connectors included as well. So you're really able to capture all of the higher order modes that happens within the interface. And we'll show a few examples, and these are actually connector approaches that we've used throughout the project. So starting with the most simple one we started out with before we had the actual connector, this kind of port is actually typically used for if you're starting, say, a transition from a package into a board. We just use coaxial ports. And essentially what happens is that you have here the connector footprint. And on the connector footprint, we add a coaxial port for the center signal. And then all of the grounds are basically shorted up to a reference sheet above. So that's the most simple port. You can use that directly in the layout tool without going into a full mechanical CAD environment. The other options would be modeling the connector as the coaxial cable. Obviously, this will only happen or only work well for structures that will look like or pretend to look, try to look as a coaxial cable. And it works really well for this particular case here. And then as we go into downloading data from the connector vendor, for instance, we could download our own model and then try to remove as many things that are not needed for the EM, such as threads and the screws and a number of other things. I mean, essentially for modeling, what you need is the transition region that's down here, as well as then the reference plane. But even if you take a model like this, if you place a port at the center here where your measurement reference plane is, that will have some limitations. And again, we'll come back and talk a bit about that. And then the highest fidelity is going to be having a model that is as assembled. This is actually not for the connector used here, but this is where we then have the actual part of the component that sits on the PCB. We have the male part that goes into that and are able to match up also with the coax cable, so we can put the port up here, but actually use the reference plane here where it would also be calibrated to in measurement, exactly where the connectors meet. And one of the things we did see previously for actually this structure I'm showing now is the microstrip via tuned. We saw there was some differences in particularly the return loss. So what I'm showing here is the return loss if we're using just a coaxial port instead of this full-blown connector model. And what you can see is that the return loss is now much better matching up against the simulations. And this is very likely due to, again, some higher order moding that is not being included in the initial setup that we had, and some tolerances that are not included. But the interesting thing also to note with this, so even if it's matching the levels, there is some differences as to where we see the peaks in the return loss. And this is an important thing to understand, that if you see ripple differences like that, it's, I mean, from a practical perspective, you probably don't care if you get this kind of good correlation. But if you want to know more about that, you would have to go in and look at the connectors and how the assumptions in the connector model actually play a role as to the dips and peaks that you see in the connector response. And this is best shown in this particular case here, where we are looking at two connectors back to back. There's the male part with the coax. There's the female part where we removed a number of the structures, just so you can see inside. Here's the actual mating interface to the PCB. And then we have another connector on the other end. And if we look at the results end to end, and I'm just going to be interested right now in the yellow and the blue curve here. In the yellow curve, we are looking at a port that was added here, and then we de-embed up to the calibration plane, versus running an extraction where we just place the port directly at the calibration plane. And that's the two curves we see here. So port at the reference plane directly, you can see you get more ripple in the insertion loss. If we look at the return loss, it looks like this structure, because the peaks are further away, it looks like it's electrically shorter. And that's actually impact of higher order modes directly at the calibration plane. So you really want to have a port away from that if you want to also capture the ripple differences here. And that will play directly a role for the overall return loss that you see. But again, as shown on the previous slide, you know, if you can get quite close on the return loss, you're probably going to be happy. But again, you want to understand where this may be coming from. The last bit we've been talking about is moding. So what does moding mean? Well, it means that when you're exciting the structure, you're trying to send through signal from one end to the other end of the structure. And what we see in this particular case is an interface where we have the transmission line here on layer 3. So it's a strip line layer. And we're plotting the magnitude of the current distributions on the plane. And you can clearly see in this channel here at 35 gigahertz, most of the energy is centered around the trace itself. But we can also see traces of moding where we see energy is actually not just in the main channel. It actually goes out from the launches out to the remaining of the structure. And so clearly, if we have a lot of energy along the edges, that energy can either be reflected back if you put the boundary too close, or, well, let's say the boundaries become more and more significant the more energy you get out. So if we'd been cutting this geometry closer, like here around the channel where we actually have wires all along, you would not have been able to capture that. And as we go to the higher frequencies, we saw especially to 50 gigahertz, or between 45 and 50 gigahertz, there was even more moding. And this is now the same channel. And what we see is that the amplitude difference between the energy in the main channel and the energy even at the boundaries here where we have a wire array is on the order of maybe 20 dB or so. So there's significantly more energy that's leaking out. And this becomes really important as you push into, say, 112G, you want to look at channel isolation. You really need to consider the entire design in its full context, or many channels in their full context, not just focusing on a single channel. So boundary conditions and cut size are really key here. A different way of looking at this, we just did a few cuts along the way. You can see the main channel here for the signal. And what we see is that at 50 gigahertz, we have energy that is, of course, radiated out from the stop itself. We have energy that goes into adjacent plane cavities, even the bottom plane cavity, and we also have surface modes that's spreading out. So in this particular case, if you want to have a thorough design up to 50 gigahertz, you really need to start looking at these kind of effects. And what's evident here is there's actually not a whole lot of bias between the launch itself and the first wire in the channel. And this is what's causing the energy to practically leak out everywhere at these frequencies. And Clarity has the capacity to run this very big structure, but also even larger structures, so you can really examine what's going on. So in summary, a robust procedure for material identification is a prerequisite for getting good measurement to simulation correspondence in the frequency ranges that we've been looking at. We've seen that the exact connector model geometry and boundary conditions are really important. And we've also seen that with a simple launch approximation, it's possible to get reasonable results for coax type launch. It's expected if you have like a multi-way connector, that assumption is gonna be less good. Moding and backdrill stop tolerance can lead to significant insertion loss variation, in this particular case beyond 30 gigahertz. And overall, Clarity is both very accurate and has high capacity for solving challenging and large designs to 50 gigahertz and beyond. Again, when you compare against measurements, you really must take care that you understand the influence of the tolerances in the design, the connectors that you should be using, the boundaries, etc. And with that, we'll go into the Q&A.